Hello and welcome to the fifth part of the video where now we are going to restore the main scope or officially called as the indicator unit. In case you were not following on, there are 4 other parts of the video where we restore the power supply, plugins, etc. etc. I've put links in the description for those videos. There is a ins video link at the end of this video as well, so in case if you like to review them. So let's understand what is inside this and how is it put together, and then we will get into the details. Okay, let's start with the front panel. Of course, this is the main CRT. Now this is probably the most key component in this whole oscilloscope, because this is technically 2 CRTs inside one bulb, because it has got 2 sets of deflection plates or 8 deflection plates, 2 beams, because it's technically 2 sets of cathodes, 2 sets of heaters, and 2 sets of deflection plates, and sharing one screen, which means there are 2 beam controls. The beams are called upper beam and lower beam, and each beam has got its own independent focus and intensity control. As you can see here as well, focus and intensity control independent for both the beams, even though they are sitting inside the same CRT. And of course the other one is the amplitude calibrator, used to generate a sample calibration pulse to calibrate your probes, or even quickly check the plugins to see if they're good. And remember, this can generate up to 100 volts pulse, so be careful. And this is a scale illumination, nothing much up there. This is the delayed trigger multiplier, which is used to select the delayed time before you start the delayed trigger. And of course you have the output for the delayed trigger right here. And for both beams you have an option to select which is your horizontal signal, which means for each beams you can select the horizontal time base from either time base A, time base B, or an external. And the same control is available here as well. You can do time base A, B, or external. This red outer knob is the horizontal position. So you have horizontal position control for 2 beams independently. Time base A goes into this plug-in bay, which is a horizontal plug-in bay. Time base B goes into the next plug-in bay. Now if you look here, they specifically say typically use 21 and typically use 22 on time base B. The reason for that is this is the only time base which is wired for delayed time base, and that's the reason you have the delayed time base trigger sitting here. Coming back down, this is the slot for the vertical plugins, the standard 500 series vertical plugin interface. That's what goes in here into these 2. So as I said before, this is the vertical, this is the horizontal for the lower beam, and this is the vertical and horizontal for the upper beam. And with the horizontal position switch, you can wire the time base in a crisscross manner so that you can use any time base for displaying your waveform. Now let's go behind this unit and see what all the connections are there. Okay, that's the rear side of the indicator unit. 3 main components, starting with the connector. This is where the power comes in from the power supply unit through the interconnecting cable, of course a fan. And let's see what this is. This is external horizontal input. You can see here we have 1 input for each beam. This is used to connect an external signal as your sweep, or an external signal as your X deflection signal. So that input gets connected here, and then there is an amplifier sitting inside the unit to amplify the signal. So of course there is a gain control for that. So the gain control is provided outside so that you can easily control the gain of the incoming external signal, so that you can adjust the sweep width, and you have it for both the beams. Coming up over here, what we have is the connection from CRT cathode. Again, we have 1 per beam. By default this is grounded. However, if you want to send intensity modulation signal to the cathode, in case you want to display graphics on the CRT, you remove the strap and plug your intensity modulation signal to the CRT cathode. That is when the switch is in the bottom position. If you're going to flip the switch on, you're going to push the CRT for dual trace chopped blanketing. If you know dual trace plugins, they have two modes of dual trace, alternate and chopped. So alternate means, let me use the fan grill as my whiteboard. Alternate means the dual trace plugin will sweep with one channel, then go to the other channel and sweep the waveform from that. So he's going to switch between two different vertical inputs and sweep one after another. This is called alternate sweep. Chopped means the trace is going to swing between both the vertical signals in the same sweep, rather than doing one complete sweep per vertical signal. And when that happens, you basically have a trace running between both your channels. And the dual trace plugins like CA provide a chopped blanketing signal, so that the swinging of the trace from one vertical input to the other is blanketed out. Or if you're using a CA plugin in chopped mode, you need to flip the switch to the other side so that your display is clean. That's about it on the rear panel. Let's look at the top side of the unit. Starting from the right hand side, what you see first is the horizontal amplifier for the lower beam, and exactly on the other side we have the horizontal amplifier for the upper beam. And what is sitting right in front of it on the left side is the amplitude calibrator, which is the port controlling the output signal level of the amplitude calibrator. And right behind that we have the high voltage cages for each beam. As I have explained before, there are two beams and both of them have independent CRT control or beam control. So there are two units which generates the high voltage. So the section for that is what is sitting right behind each of the high voltage cages, the high voltage oscillator tubes and the associated control circuitry. And if you see, the cage size for the high voltage is different for the upper beam and the lower beam. The lower beam has got a bigger high voltage cage compared to the upper beam. The reason for the lower beam high voltage cage being bigger is the lower beam high voltage section is what provides the anode voltage to the CRT. If you see this high voltage cable, that's what gets plugged all the way into the CRT anode right down here. So the additional voltage doubler needed to do that is built as part of the lower beam high voltage cage or high voltage section. Let's see what is inside this. That's the unit with the high voltage protection shield off. These are 5642 diodes which are used as high voltage rectifiers, and this is the high voltage transformer. You can see this one sitting here. This provides the high voltage which gets rectified and used for controlling the grids in the CRT, and one section gets doubled and fed all the way into the CRT anode. And this is for the upper beam, which is quite simple because there is only one voltage which is kind of one or two voltage which is delivered out of it and filtered and used to control the CRT grids, and that is the high voltage transformer for the upper beam. So let's get inside the unit and understand some of the key components. Let's go all the way back. The plate voltages and basically all the power supply comes into the chassis through the interconnecting cable to the back side of the unit, and the fan is directly powered from AC, and rest of the plate voltages are also bought in. These set of capacitors, what you see, 6 of them are mainly the decoupling capacitors. There are other decoupling capacitors in the chassis, like this one sitting next to the horizontal amplifier. Moving on, this is the main heater transformer. This is a transformer which powers all the filaments in the chassis. As I've explained in the power supply video, the input to this transformer is regulated so that the heater voltage is also regulated. Moving on to the next step, let's see how each beam is processing the signals. So let's start with the right hand side, which is called as the lower beam. Let's look at the vertical signal first. The vertical plug-in gets plugged in here, and that provides the differential vertical signal, which is processed by the plug-in into this connector, and that comes in straight into the vertical amplifier at the back of it. These are the front-end drivers for the vertical amplifier, and what you see here is the main vertical amplifier, which is a distributed amplifier done using a 6DK6 farm, and the output of that goes into the delay line right here. And the delay line then sits all the way through here, and at the end of the delay line, the signal actually gets passed into the vertical deflection plate for the lower beam right into the CRT here. Let's go and look at the upper beam now. This is the upper beam signal path, exactly like what we saw on the other side. For the lower beam, the vertical input connector. The vertical input connector passes to the vertical amplifier sitting right behind it, the distributed amplifier, the delay line, and then the delay line processes or adds the delay and then plugs the signal directly out into the vertical deflection plate. That's the vertical deflection plate connection for the upper beam. This is the schematic for the vertical deflection amplifier. This is a distributed amplifier, which basically means this is not cascaded. When you say cascading, the output of one stage drives the input of the next stage of the amplifier. This is not a cascaded amplifier. This is a distributed amplifier where the outputs are added from multiple sections to generate the gain you need without compromising the rise time or the bandwidth of the amplifier. Now, the detailed working principle of a distributed amplifier is beyond the scope of this video. However, there is a very good article in TechWiki about it. I will link it in the description below. Next is the horizontal or time-based processing. So the type 22 plugin comes in here. This is again for lower beam. The plugin passes the horizontal sweep signal here, which gets into the actual sweep processing stage here. Now, technically, this is two components. This portion is an amplifier, which is used to amplify the horizontal input signal, the external horizontal input signal, which is coming in from the rear of the chassis, as we have seen before. So there's a small tube sitting here to amplify that signal. In addition to that, this is the delayed trigger pickup circuitry. This is what processes the delayed trigger. And this is available only in the lower beam. That's the reason they suggest that you put the type 22 plugin here into the lower beam so that you can use the delayed trigger control here as well. So signal is passed to the time-based selector for lower beam, which is this particular switch, what you see here, horizontal display selector switch. So he selects which is the horizontal input for the lower beam and passes that into the horizontal amplifier, which is sitting right on top here. And this horizontal amplifier amplifies the signal and passes it out into the horizontal deflection plates. What you see here, these connections are going straight into the horizontal deflection plates for the lower beam. And these are the tubes for the horizontal deflection amplifier. Coming back to upper beam, almost the same signal flow. The plugin, the horizontal plugin for the upper beam, generates a sweep and passes it straight into the switch, technically, because there is no delayed trigger processing for the upper beam. And this is the external horizontal amplifier to amplify the external horizontal signal, passes it straight to the time-based selector switch, or as we see on the other beam, the horizontal display selector switch. And this switch selects a sweep for the upper beam and passes the signal straight to the horizontal amplifier, which is sitting straight here. And he amplifies the incoming signal and passes it straight to the horizontal deflection plates for the upper beam. This is the schematic for the horizontal amplifier. Both the sections have a similar horizontal amplifier schematic and layout. So we will just explain one. It's very simple compared to the sweep section what we have seen. However, the design is extremely complicated and there is much more details into it from a design perspective to achieve a consistently linear sweep across the supported frequency spectrum. But from our perspective, we will cover it at a high level to understand how it works. So let's start from the source of the signal. This is where the input signal is coming in from the horizontal time-based selection switch, and that is fed to the first cathode follower. And the output of that is fed through the sweep length multiplier or sweep magnifier switch, which is nothing but it short circuits the resistor which is in series when you switch on the magnification. and then feeds the input to the next cathode follower. And from there, it is fed into the paraphase amplifier, which are these two tubes right here. If you wonder why the paraphase amplifier or differential signals are used all throughout the horizontal and vertical section, the main reason for that is the plates are driven always with a differential signal. So the paraphase amplifier then provides the output to the next stage, which is the final driver amplifier, or what you call as the cathode follower, and that is connected to the plates sitting right down here. This is the deflection plate, I would call it as. And that's the signal. It's already marked here. Now, this is one tube. If you observe this is the first thing which caught my attention when I first started working on the horizontal section of oscilloscopes, tech scopes basically. So let me cover that quickly. If you look at the horizontal deflection plates, they are technically a capacitor sitting at the output of this amplifier. So at extremely high sweep rates, what's going to happen is this capacitor, or the deflection plate, what you call as a deflection plate capacitor, starts charging and discharging with the sweep rate. And if you look at the signals, this is the negative side of the differential signal and this is the positive side of the differential signal. Because if you see, this is what goes up and this is what goes down. So what happens if the sweep rate is too high? When the sweep comes down, this capacitor is trying to discharge. And in case if this tube is not able to provide sufficient current for this capacitor to discharge, when I say capacitor, the deflection plates, the capacitor created by the deflection plates, if that is not able to discharge faster, it will drive this final output tube to cut off. That's why they have this tube sitting here, which is in fact called as a high frequency capacitance driver. What it does is this high frequency capacitance driver tube is actually driven by the positive side of the sweep, and that is directly sitting in the cathode of the final output triode. And what it does is, on high frequency ramps, it can provide an additional shunting path to discharge the capacitor on the negative going side, and that's why it's called as a high frequency capacitance driver. This is the amplitude calibrator selector port and the multi-vibrator circuit supporting it. Basically generates a square wave pulse to calibrate your probe, and that's this portion of the circuitry. This is the high voltage oscillator and the control circuitry for upper beam. The tube for that are sitting right underneath here. The right hand side where the high voltage oscillator for the lower beam is sitting, these two tubes, and they are again hidden deep underneath the chassis right here. Let's look at the CRT section of the schematic. Let's start from the star of the show, the main dual beam CRT. If you look at it, you can see this is technically two CRTs in one, or rather two guns, two filaments, two cathodes, and two sets of control grids, as you can see here. And both of them are driven separately by their own high voltage oscillator. Let's look at the high voltage oscillator side. This is the primary side of the oscillator, which is controlled by the HV oscillator tube 6CZ5, and that is in turn controlled by the feedback amplifier, which uses two triodes, which is 112AU7, and the feedback voltage is picked up from the output, as you can see here. That's why this is the high voltage adjust point. So, and the main transformer is powered from unregulated 330 volt. The reason for that is you have regulation here anyways. And this is exactly the same on the lower beam as well. The same tube, same set of feedback amplifier arrangement, and this connection is actually not shown in this scan, but it actually comes here for high voltage adjust port. Now, output of this is used to control or generate all the high voltages. So one secondary is taken out, used for the first control grid of the CRT for both the beams. You can see here as well, all the way right. Yeah. That's where your intensity control is sitting for both the guns or beams, so called. The unblankening signal from the sweep generator is coupled here as well. This is to disable the retrace for the beam. The second high voltage output is generated and used for focus control, and that is what is coming out of this section of the circuit, and that is being biased directly to the cathode, and that's where your focus controller is sitting. And it's exactly the same for the other gun as well, if you trace the schematic. Now the extra part which you have in the lower beam high voltage section is this voltage multiplier, which is used to supply the plus or positive high voltage out into the CRT anode. Now, when I say CRT anode, this is again another specific Tektronix thing. It's actually called as a post-deflection acceleration helix. If you see the photos of the CRT, you can see that it's a spiral coating inside the CRT with a resistive material. I guess that's the reason they show the symbol as a resistor right down here. So that is again used to achieve some very specific CRT qualities and beam qualities rather, and keep the high voltages at a control limit. Again, the discussions into that is beyond the scope of this video, but there is information available in TechWiki in case if you're interested. One more word of caution in case if you're working on it. You may be familiar with this already, but I'm just warning you again. These controls, this is the focus and intensity control for each beam. This is actually behind the front panel. Be careful. They are supplied from the high voltage power supply. So be careful while working on this. Do not, poke around in these controls. This is the underside of the chassis, and this is where the power comes in from the power supply through the cable and hits the main transformer for the heater voltage, and rest of the plate voltages are directly distributed. Here you can see the plugins, the vertical plugins driving the vertical amplifier directly, and this is for the other beam, again from the plugin directly driving the vertical amplifier, and the line driver circuits for the grid and plate side of the distributed amplifier. And these are the main power supply filter capacitors and the associated passives around this. So now I'm going to get in, find, replace or reform all the capacitors. I'll explain you what I mean by find when we get there. Also, I'll test all the tubes, and we will continue from there once I'm done with that. A quick look at the decoupling network or the power supply decoupling network. There's a whole bunch of capacitors. They are spread all over the chassis. They usually sit next to the function which they are supporting. So you can see plus 100 volt for each rail. There is a dedicated decoupling network. So these are the capacitors which we need to test and make sure that they're good. Trying to show you how painful the whole reforming process is. Here, for example, just to access this capacitor, I have to lift the components around it, mark the ceramic strip from where the connections or the leads are coming in, disconnect it, and then try to test it. So that's a whole process which I'm following for the entire set of capacitors. This is how I go through the part list and test each capacitor and mark whichever needs to be replaced. In case if you're wondering why do I rigorously go through all the list and check capacitors out, this is an example where there could be capacitors hidden somewhere far deep inside the chassis like this. It's not just one, but there are two capacitors, one on top as well. And here is another one buried deep here. This is one of the 6.25 microfarad 300 volt capacitors in the horizontal amplifier, which you can't figure out unless you trace the circuit. And this is how you should not, I repeat, you should not reform your capacitor. That's the switch mode power supply which I'm using for reforming power. Comes out, goes into a highly secure current limiting resistor, which is properly mounted and installed and secured, and that drives through a potentially well insulated cable connection flying through this and into the capacitor being reformed right here, and the ground return goes all the way through another secured connector back through a very insulated cable lines into the meter which is monitoring the leakage current and all the way back through a very well organized cabling back into the power supply. So that is how you should not reform your capacitor. I was able to reform all the capacitors except one decoupling capacitor, which is two 15 microfarad 450 or no 350 volts capacitor, which is the decoupling capacitor for the horizontal amplifier. This guy is bad. It is leaking pretty heavily, so I had to replace it. Unfortunately, I didn't have a 16 or a 22 microfarad, so I had to put two 10 microfarad, which is 20 microfarad for each one of them. So that's the reason I test all the capacitors, because you never know, there could be just one which is bad. In case if you're wondering why I did not test these capacitors, they all are film caps, so they're not paper, so I need not test them. Still to confirm, sometimes you never know, the packaging could be misleading. So still to confirm, I usually pick one and test it to make sure that it's not a paper type, or some other type of molded paper. Damage report from the tube testing department. Both the high voltage oscillator tubes 6CZ5 are short, and two 6DJ8s from the horizontal amplifier, again same problem. So I have to replace them. I have the 6DJ8s, but I don't have the 6CZ5s in my stock, so I need to source them, and then we will continue. So I've tested all the tubes, replaced all the capacitors as you've seen, and what I've done is I put a suicide cord into the primary of the heater transformer directly underneath the chassis, and I've applied some voltage onto it, like about 70 volts, to see if all the tubes are lighting up, and maybe give it a warm-up as well. It's too bright for you to see what's going on. Let me switch off the light so that you kind of get to see the show. That's the 6DK6 farm lit up, and the view from here is magnificent, I should admit. That's the other side of it. In case if you're wondering what is a suicide cord, this is what it is. Easy way to power up anything in the most safest manner. Okay, I'm all set for the first power up. I've hooked the power supply and the indicator unit together, and also hooked two multimeters to the test point for minus 150 volt and the heater, which are these 2 points wired to 2 multimeters sitting here. Of course, I'm not using variac because I've already tried that on the power supply and I know it's all good. Plus there is a time delay relay, so there is no way I can really control it. So as a pre-power up settings, I've kept the intensity on both the beam to minimum, so that just in case if it comes up with any broken controls or the biasing, I don't want these guys to burn the screen. Both horizontal selector for each beam has been put to their respective time base. Say this is upper beam, which is marked into time base A, and this is the lower beam, which is mapped to time base B. Both of them are set to normal trigger, and the trigger source is selected as line because I know the line definitely will have the trigger, and the trigger level at midpoint, and vertical position at midpoint for both the beams. So do the horizontal position is also at midpoint for both the beams, and that's about it. And I'm going to power it up, and all we need to do is wait for the click. Okay, it did click, and I do see a minus 145 volt, which is slightly lower, and the heater voltage is slightly high. It's at 7.15 instead of 6.3, which I need to adjust down below. And let's see how's the beam responding. Oh, okay, I have one beam. Position control is good. Let me adjust the vertical position. Okay, that's also good. Let me reduce the intensity. Let me try the other beam. Okay, that seems to be doing something, but not a trace. Nope, upper beam seems to be not tracing. And oh yeah, there is no time base. So if you switch to time base A for the other beam, it's dead. That means if I go here and switch to time base B, oh yeah, there you go. So time base A is dead. I do have horizontal position control. Let me see if I have vertical position control. Nope. And yeah, intensity control seems to be working. And yeah, focus is also there. I'm not very happy with the upper beam controls. It seems to be a little bit erratic. Okay, maybe it's a dirty pot. Yeah, this all the way looks like a dirty pot, unless there is something wrong with the... No, it looks like a pot which needs cleaning. Maybe I missed it. And yeah, time base A is dead. No sweep at all. So if I switch to time base B, I do get a trace for the upper beam. So time base A, this guy is dead. Anyway, the voltage is low, so I'm not going to do much until I adjust the power supply voltages. But overall, nothing is smoking at least. Let me see if I can measure some other voltages. 96, 211, 338, 486, 54. I'm not sure what that is. So these are the main power supply testing rails. This is minus 150. This seems to be plus 100. This is plus 225. This is plus 350. And this is plus 500. That's what I'm looking at this meter. So all of them are low because of minus 150 is low. Now the heater is at 6.27, which is okay. I'll leave it at this level for some time until I fix everything else. And let me adjust the minus 150 now, which is pretty easy right outside here. So minus 150 is intact. So now let me check all the power rails since my minus 150 is in shape. I'm going to go through each one of these test points, and you can see the multimeter reading as I test it. Starting with minus 150, perfect. Plus 100, 99.4, 223. Needs to be slightly higher, 348 for 350 and 496 for 500 volts. So I'll check the tolerances and see how far is the tolerance or allowed tolerance limits, and then we will come back. So at this point in time, the number one problem what we have is this time base being dead. So that's probably what is causing rest all issues, I would believe, or we don't know.